In this example, we're going to determine whether or not each of these relations represents a function. So before watching this example video, make sure that you've read the text and you understand the definition of a function and that you already have that written into your notes. So first of all, we need to know that a function takes each input value to exactly only one output value. And that's really the key meaning behind a function. Each input goes to only one output. And in this case, we usually use X for input and Y for output. However, sometimes that can change. So just be aware of what is representing your input variable and what is representing the output. Okay, so relations can be represented in a variety of ways. In the first part here, part A, I have a relation being represented with a list of ordered pairs. So we know in ordered pairs, it's an X comma Y. X is the input and Y is the output. So off to the side, I'm going to write a note that in an ordered pair, input comma output. Okay, so in the definition of a function, each input can only go to one output. So here we have 2 going to 6, which 2 goes to one number. -3 goes to 6, so -3 is only going to one number. 4 goes to 9, and 2 goes to 10. So in this first example, we actually have a problem with the first ordered pair and the second, because these two ordered pairs tell me that when I input 2 into this relation, I will either get out 6 or 10. And that's a problem when it comes to a function, because when I'm using a function, I really want my input to only give me one output. And in this case, the input of 2 has 2 outputs, 6 and 10. So for part A, this is not a function, because the input value 2 is linked to 2 output values, 6 and 10. And the problem here is that it's linked to 2 different output values. It should only be linked to 1. So I can also represent a relation using a mapping, like here in part B. So I have a set in this box and I have a set in this box, and the way I'm demonstrating the relationship between input and output is with these arrows. And I know that this set is representing inputs because the arrows are pointing away, and these are outputs because it's telling me where the inputs go. All right. So in this example, we have A mapped to one value, which is good. B is mapped to one value, which is good. C is mapped to one value, and D is mapped to one value. So each of these letters here is associated with only one number. Now the question becomes, is it okay for B and C to both be linked to the same number? And the answer is yes. So this right here, B goes to 3 and C goes to 3, is a-okay. Now, here's how I like to remember this distinction, is that my friend and I can both go to the same restaurant. However, I cannot be at 2 different restaurants at the same time. So this input number 2 representing myself, I could not be at 2 different restaurants at the same time. But myself and a different person, so 2 different inputs, right, could both show up at the same restaurant, and that would be fine. So what matters here is that each input is only pointing towards one output. That definitely is a function. Okay, so where it gets a little more difficult is if you're looking at a relation that is being expressed using an equation. And since this is a math class, we'll mostly be working with equations. So I have two examples here to investigate, part C and part D. The question is the same, do these represent functions or not? So when you're working with equations and you're asked this question, the easiest way to answer it is to first figure out which one is your dependent variable, okay? And in this example, I'm looking for y as a function of x. And this phrasing right here tells me that y is the dependent variable. Right? Y depends on x. So what I want to do is actually solve each of these equations for the dependent variable. Now, like I said before, x and y might interchange, or you could see an equation with two completely different letters like alpha and beta. So you need to pay attention to the phrasing in the question to determine which of those letters is the dependent variable. Once you know which letter that is, solve the equation for that dependent variable. If you can easily solve the equation for that dependent variable, then that's your first opportunity to determine whether or not it is a function. So let's just work with part C right now. Y is already solved for, which is a good sign. That's not the only thing we're going to check, but it's a good sign. The second thing I want to look for is if I plug in different values of x, will I really only get one y? So I might try a few values. Let's try 1. Okay, if I plug in 1 for x, will I get only one number for y? Simplify. And yes, I got one value for y. I might try a bunch of different numbers. What if I plugged in a negative? What if I plugged in a fraction? What if I plugged in 0, etc., until I notice that each x I plug in will only give me one y value, which means this is definitely a function. And not just any function, but it represents this phrasing right here, y as a function of x. Awesome. So in part D, I'm going to try the same thing, except over here, y isn't solved for. In fact, x is solved for. So what I'm going to do is solve this equation for y, my dependent variable. So in order to isolate y, I will take the square root of both sides. And since I'm square rooting variables, I can't forget my square root property. So I have solved for y, and I easily did that, so that's a good sign so far, but it's not the only test. So what I need to do now is try some different values of x and make sure that I actually get one y value. So let's try 1. Okay, I'm going to draw a line here to separate between my two parts. Okay, so if I plug in 1 for x, then y is plus or minus the square root of 1, which means y is equal to plus or minus 1. And that plus or minus notation is shorthand for two values. This says y is either positive 1 or y is negative 1, which means one x value goes to two y values, which means this does not represent a function.